Good morning, this is your Stat Sensei, Mr. Spensei, and this is the Death Packet, Chi-squared, and Regression. We'll be focusing on problems 21 through 30, which are for regression. So data on the number of cancer deaths among Americans in the thousands and years since 2001 result in the regression line. Deaths equals 550 minus 6.05 years with R equal 0.863. What is the correct interpretation of the slope? All right, so let's talk about that real quickly. So with slope, we know it's going to be the y over x, as we learned that in uh, algebra 1. So deaths is our y, and years is our x's. So in this case, we're going to have death over years, and we know it's negative 6.05. I should rewrite that where I have more room. Negative 6.05 deaths for 1 year. All right. So, but this is in the thousands, so I need to multiply this 6.05 times 1,000. All right. So when I do that, that ends up being negative 6,050 deaths per year. So, what I see happening as the number of deaths from cancer is decreasing for every 1 year. So, we're expecting 6,000 less deaths every year. All right. So, the number of cancer deaths among has been dropping by an average. That's a key word. It's not by specifically, but by an average of 6,050 deaths. Because this is, remember, we are working with averages when we talk about this. So our best answer choice for 21 is A. For 22, which of the following is a high leverage point with respect to the regression? Well, a high leverage point means we are substantially different in the x direction. Well, here's our x direction, and the value that seems to be way off in the x direction is this one right here. So I'm going to say that it looks like 80 and about 70 is a high leverage point. This has the largest residual, and because it has such a large residual, it might be an outlier. Not sure, but the difference from the prediction, as that gets big, that's an outlier, but a big difference in the x direction. So when we're looking for changes in the x direction, then we're talking about high leverage. So our best choice is E, which is 80 and 70, which is that point right there. All right, moving on to 23. A restaurant manager collected data to predict monthly sales for the restaurant from monthly advertising expenses. So we need to think about this real quickly. They want to predict monthly sales from monthly advertising. So they're saying, hey, what's sales? That's what we're predicting using advertising. So that means advertising, this is our Y, this is our X. And what we would expect is we'd expect sales to go up or increase as advertising goes up. We'd expect a positive correlation. All right, so we're going to expect it, and they gave us all positive answers. If they'd given us a negative answer, we could probably eliminate it because we'd expect sales to increase as advertising increases. All right, the model showed that 36% of the variation from monthly scales could be explained by advertising expenses. So our R squared equals 0.36, and they're asking for the value of the correlation coefficient. So if I just take the square root of of 36 or raise it to the half power, I get 0.6. So R equals 0.6. I look at my slope and I'm expecting to have a positive slope. So this should be a positive 0.60. Please make sure you always pay attention to what the slope is. All right, but in this case, we'd expect sales to go up as advertising increased. Suppose the correlation between two variables is 0.85. If each of the y variables is multiplied by -1, what is true about the scatter plot? Okay, so our correlation is going to change, is going to be the same, but we had a positive correlation. We were increasing, but now we're multiplying by a negative, so we'll end up with the same correlation, but we change the direction from a positive 0.85 to a negative 0.85. And by the way, this should have fairly tight data points to the regression line. So we're expecting to have sloping down and to the right because our direction changed because we only multiplied one of the variables by -1. If we multiplied both by the -1, it would have remained the same. All right, number 25. A researcher in Alaska measured the age in months and weight in pounds of a random sample of adolescent moose. When the least squared regression line was performed, the correlation was 0.59. Which of the following is the correct way to label correlation? Well, this is a weird one. This is one time when a value does not have labels with it. So correlation, so R equals 0.59. It's a positive 0.59. It's not pounds. It's not per month. It's just 0.59. It has no labels. So correlation has no labels. 26. A family would like to build a linear regression equation to predict the amount of grain harvested per acre of land on the farm. They subdivide their land into several smaller plots of land for testing and would like to select an explanatory variable they can control. Okay, so this is important that they can control. Which of the following is an appropriate explanatory variable that the family could use to create a linear regression equation? Total amount of rainfall. Be nice, but they can't control it. The type of crop planted in the plot for the previous year. That's not going to do what we're looking for. That's from the previous year. The average daily temperature, can't control it. The variety of grain planted in the plot, that varies, but we probably want to hold that constant so we can sit there, and we probably want this to be our our output. We would like this to be our output or our response variable. So that's not what we're looking at. That's not what we want our response, our explanatory. Our best explanatory variable would be fertilizer. So if we vary the amount of fertilizer, if we add fertilizer, how much does our crop increase, or does it increase, or how much does it vary? So the best explanatory variable that we can control would be E, fertilizer. As exponential relationship and an exponential relationship between the explanatory variable and the response variable in a set of data, the common logarithm of each value of the response variable is taken, and the least squared regression line has an equation of log of y hat equals 7.3 minus 1.5x. Which of the following is closest to the predicted value of the response variable when x equals 4.8? So we're going to have log of y hat equals 7.3 minus 1.5 times 4.8. So when I plug that into the calculator, I'm going to go 7.3 minus 1.5 times 4.8, and I end up getting 0.1. So the log of y hat equals 0.1. But that's not what I want. I don't want the log of y hat. I want y hat. Well, to do that, I can do that everything by raising it, by taking this and going, well, if I go 10, and it'll always be 10 because it's a common logarithm, and raise it to the 0.1. So let's do that. 10 raised to the 0.1 power, and we get 1.2589. And my closest answer to that is D, which is 1.26. All right, 28. For a random sample of 20 professional athletes, there's a strong linear relationship between the number of hours they exercise and their resting heart rate. For the athletes in the sample who's exercised more hours per week tend to have lower heart rates. So let's go ahead and do this. All right. This is hours, and this is heart rate. And they say the more I exercise, it starts to decrease. All right. So that's what it looks like. So in this case, I know I'm going to be dealing with a negative because it told me it's decreasing. All right. They have lower. So as this goes up, as hours go up, heart rate goes down. So they're in opposite directions. So we have a negative relationship. Well, that immediately gets rid of those two. Well, then they tell me I have a strong. Well, this is obviously weak. So the question is between D and E. Is it likely that they have a perfect linear relationship, especially when they use the word strong? Not likely. It's not likely they have a perfect linear relationship. And negative 0.87 is definitely a strong relationship. All right. Anything above with a value of 0.75 or more is going to be a strong relationship. All right. 29. The least squares of a regression line S hat equals 0.5 plus 1 minus 0.1 L models the relationship between the listing and the actual sales price. All right, so please remember that when we're doing this, and they're going to ask about the slope, which of the following is the best interpretation of the slope? Well, our slope, or B, is going to equal, remember it's it's always Y over X. So in this case, sales price over listing price. And there'll be a 1.1 increase in sales price for every dollar increase in listing price. All right. So for each 100,000, and by this is what we predict, or this is what we'd expect on average. So the sales price will increase. I don't like the word will. All right. And it's not going to increase by one, it's 0.1. It's going to be increased by 1.1 times 100,000. All right. So that one's wrong. So for each 100,000 increase in a listing price of sales will, I don't like that word, increase by 110,000. So I don't like that word will. Let's see if there's something better. For each $100,000 increase the listing price, the sales price will decrease. No, we have a positive slope, so it's not going to decrease. It's going to increase. And we don't like the word will. So the C is definitely wrong. For each $100,000 increase in listing prices, sales price is predicted to increase by 1.1. No, it's 1.1 times 100,000. So that one's good, not right. For each $100,000 increase in listing prices, sales is predicted or expected, or on average, we believe it will increase by 110,000. That's our best answer choice. Be careful about the will and predicted or on average. Okay. All right. Number 30. A tennis ball was thrown in the air. The height of the ball from the ground was recorded every millisecond from the time it was thrown until it reached the height at which it was thrown. The correlation between the time and height was computed to be 0. What does the correlation suggest about between time and height? Well, if you know anything about throwing a ball, it's going to have a parabolic shape. Okay? So there's definitely a relationship, but so we can't say there is no relationship. There is a relationship. It's going to be shaped like a parabola, but there is no linear relationship. And even if we didn't know a shape like this, we go, well, there could be some relationship. We don't know what it is, but there's not a linear relationship. All right, because basically we throw the ball, it goes up and then it comes back down. And this would be the height here, and this would be time here. So as time increases, the ball gets higher and higher, and then it starts to come back and gets lower and lower till it gets to the point from which it was thrown at. All right, I hope that helped, and look forward to seeing you on the next one. Thank you.